Assalamu alaikum wa rahmatullah. I'm Dr. Mohammed Rashah, and this is my new class on distributed and parallel computing. So please find all videos on my YouTube channel, and don't forget to subscribe and like if you want. Also, don't forget to click the bell to receive all new updates about the newly uploaded videos. Today, actually, I'm going to go through quick introduction to parallel computing. So in today, we are not going to take too much things actually, but only the concept of parallel computing. Only the concept of parallel computing and how we can get some scenarios or some problems from the real life and how to convert it to parallel problems and later to be ready for parallel programming. Okay, so this is the purpose of today's class. Okay, also for today's class, it's going to be short, so maybe we can finish before the time ends. Then tomorrow, inshallah, we continue from where we stopped on. For today, inshallah, we will talk about what is parallel computing and why parallel computing. So we need to know what is the parallel computing and why we need to use it. Okay? Okay, first, what is parallel computing? Anyone of you has an idea about the parallel computing? What does it mean in general? I don't want you to give me any complicated or very detailed answer. In general, do anyone of you have a knowledge about what is the parallel computing?
No.
No clue at all. Okay, basically, very basic concept actually. The parallel computing is to do computing for multiple things at the same time. Okay, is that clear?
Right, like multitasking, is it?
Yeah, actually multitasking need to have parallel computing. Otherwise, we cannot have multitasking. Yeah, multitasking is one of the applications or the results of the parallel computing. If we don't have parallel computing, then we never have something called multitasking operating systems like Android or maybe iOS or maybe Windows or Linux, because all of that operating systems are multitasking. So if multitasking means we need to run multiple tasks at the same time. So this is the key of the parallel computing. So again, parallel computing is how to run multiple tasks or multiple processes at the same time. Okay. Before I go to why parallel computing, actually, or even before I go through the slides, I want to tell you about something which is very, very important for real life parallel programming or parallel computing. Actually, in our life, we have many types of problems, But this many problems can be categorized into two main categories in general. Okay, the first category is serial problems, and the second category is parallel or concurrent problems. So the serial problems cannot be solved using parallel computing, because if we try to solve serial problems using parallel computing, that will add extra overhead, then it will bring more delay, it may hold unnecessary resources for nothing. Okay, because the purpose of having parallel computing is to increase the speed of computing, or to increase the speed of solving issues. Okay, to increase speed of solving issues. So how to increase the speed of solving issues is by calculating or computing things faster. How we can compute things faster? Maybe we need to break them into multiple partitions, then we solve every partition in different thread or maybe on a different processor. Okay, so in this case, if the nature of the problem is concurrent or parallel, so we can solve it using parallel computing. But if the nature of the problem is serial, then there is no point to use parallel computing. So before this, before we use parallel programming, we have to decide, we have to understand the nature of our problem. Then we have to decide whether to use sequential programming or to use parallel programming. Okay? Is that clear, guys?
Yes.
Okay, so as I said, everything is based on the nature of the problem. Okay, later I will give you some scenarios, small scenarios to understand. Okay?
Okay.
Take this down here and we see how to find some issues. Okay. Okay, yeah, let us go to the next slide here, and we see what is parallel computing. So traditionally, software has been written for serial computations. So this is what we have last time when the computers just started and entered the market. So at that point of time, all computing available in the market was serial based. So multi-processing was not possible because the infrastructure, the software, the hardware, everything was not designed for solving parallel issues. Okay, so even if the nature of the problem is parallel or concurrent, at that time they was changing it to a serial, converted to a serial, a serial problem. They put it in a queue, then after that they try to solve it sequentially one by one. Okay? So traditionally, as I said, software has been written for serial computation to be run on a single computer having a single central processing unit, because last time we had only a single CPU in every computer. But now, alhamdulillah, we have many types of computers and also many types of processors, many types of memories. We can have in our laptops, we can have i7 or i9 or dual core or multi-core or whatever processor we need. So all of that processor types can handle parallel computing because they have multi-threads, at least multi-threading processors. Okay. Later we will talk about what's the meaning of multi-threads and what's the meaning of the thread. Okay. Also, many computers or many CPUs has multi-cores inside, so that cores will act like real CPUs. Okay, and also some architectures that have only single physical processor can work as a multiple number of virtual processors. Okay, so also that one can handle parallel programming. So that's why now we can handle parallel programming, but last time everything was serial because we had only a single CPU machines or single CPU computers. Also, the problem is broken into discrete series of instructions, as you can see here in the graph, in the diagram here. So if this is the problem, so the problem will be divided or will be broken into discrete series of instructions. So every instruction will be computed in the CPU. how the entire number of instructions is going to be computed at the CPU, it will be one by one, sequentially. Okay, so instructions are executed one after another. Only one instruction may execute at any moment of time. So at any moment of time, at the CPU, we will have only one transaction or one instruction. Okay, at the CPU, at any point of time, we will have only one instruction. Okay. Okay, let us take an example here. So if let's say we have vectorial x, for example, or vectorial 10. You know what's the meaning of vectorial? Do you know the meaning of vectorial?
It's 10 times 9 times and so on.
Yes, correct. So this thing actually is going to be, I don't know why it flips over. Okay, 10 vectorial equals 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Definitely no times 0. Okay, so until 1. Because if we multiply by 0, then the result will become 0, and we have we lose our the value of our vectorial. Okay, so here, in order to solve this problem, actually, we have to send the instructions one by one. So at first we send this, then this will get the result 90 here, right? Then after that we take 90 times 8. It will give us a number. Okay, then we take that number, we give it to the processor times 7. Then after that the result will be given to the processor as the x times 6. Then the result of that will be given again after that to the processor. So how many cycles we have here is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9 cycles. So in this case, here is the direction of the time, right? This is the direction of time. Okay, so if let's say, for example, if the time of completing one instruction like this is, for example, 2, for example, only to understand, for reality is different. For example, this one is 2 seconds. So in this case, how many or how long we need to complete the processing of the 10 vectorial? So here it will be 2 seconds times 1, 2, 3, 4, 5, 6 until 10. It will be 20 seconds, for example. Okay, so in this case, time cannot be reduced. If we have a single processor machine, time cannot be reduced. Why? Because the processor can take only one instruction at a time. Can take only one instruction at a time. Okay. What if we have 2 processors? I'm going to jump, okay? Because now I'm not going to follow the slides, because I want you, my target is only to make you understand, not to follow the slides, okay? So I don't care about the slides. My responsibility is to explain to you every small piece of thing here. Okay, so if let's say we have 2 processors, the thing that we can do is to break this into 2 chunks. Okay, so this to be given to CPU number 1, and the other one should be given to CPU number 2. Okay, is that clear, guys? Because here the sequence of calculation, because the nature of the problem here, it's not matter to multiply 10 by 9 first or 7 by 8 first. It's not a problem. You can multiply 1 by 2, then times 3, then you can jump to times 7, you can jump back to times 4, whatever. The sequence is not a matter here, right? The ordering, I mean, of the operations or the order of instructions is not a matter. That's why the nature of this problem actually can be concurrent, can be solved based on parallel computing. Okay, so in this case, we can, if suppose that we have two processes or two processors, two CPUs in our computer. So the first CPU will take the first partition or the first chunk of the problem, then the second processor will take the second chunk. So here we have multi-processors with multi-data, right? Or maybe multi-processors with single data. So every processor will have a single data. Okay, these details actually will be explained later. I'm not going to explain to you what is the meaning of that now, because later we are going to take a complete portion of the material in this course about that architecture. So we have single processor with single data. We have a single processor with multiple data. We have multiple processors with single data, multiple processors with multiple data, and many things. Okay, later we are going to explain that on its time. Okay, so here what we have to do, if we have two CPUs, we divide the things, or we break the entire problem into two main sub-problems. So the first sub-problem is from 10 to 6, the second sub-problem is from 5 to 1. So here the first CPU will take from 10 to 6, the second CPU will take from 5 to 1, and both of the CPUs will work at the same time. So if, let's say, as I explained at first, if let's say this is the first instruction, then the result will be multiplied by 8, then the result will be multiplied by 7, then the result will be multiplied by 6. So in this case, how many cycles we have? We have 1, 2, 3, 4 cycles, right? And also here we have 4 cycles. So if, let's say, every instruction consumes 2 seconds, in this case here we have only 4 seconds, right? 8 seconds. 8 seconds here and 8 seconds here. Okay, then after we got the result, if let's say this one is x1 and this one is x2, which is the result of the operation here, the first problem and the second problem, then after that we have to multiply x1 by x2 to get the final result, which is the 10 victorial. Okay, so in here this is also another instruction, right? So this instruction will cost 2 seconds. So 8 seconds plus 8 seconds is 16 plus 2 is 18, while the first one consumes 20, right? 20 seconds. So here we saved only 2 seconds. Why? Because we take only a very small problem. But if let's say we have a billion, the victorial of billion, so in that case we will see how the time is going to be reduced. And also, if let's say we have more than 2 CPUs, then if let's say we have 16 CPUs, then we can divide that big problem into 16 chunks. Then every chunk is given to a single CPU. Then the time will be divided by 16. So we will save about what they call it, 15/16 of the time. Okay, so that will be a huge improvement and huge acceleration of solving problems. Okay, Actually, parallel computing is not for the simple problems. Is not for the simple problems, because the parallel computing will introduce other overhead. Actually, it will introduce extra overhead to handle the threads, to create some sub problems. Maybe you need sub variables or whatever. Then after that you have to collect the sub results. Then you have to combine them together to get the result of the main problem, and so on. So that is called parallelism overhead. Parallelism overhead. So in the real life, if the parallelism overhead is more than the significance of the problem, then we better solve it in sequential manner. Okay? We better solve it in sequential manner. Okay? Is that clear, guys?
Clear.
Yes.
Yeah.
But Dr. I have one question.
Yeah.
So if I have two CPUs, will the first chunk and the second chunk run simultaneously?
Mm-hmm.
Oh,
Yeah.
okay.
Yeah. Yeah. If we have separated CPUs, then every CPU can work independently, and also both of them can work simultaneously at the same time. Okay, so that's why the architectures of today's computers supports very heavy parallelism or very heavy parallel computing systems and designs. Okay, so for very huge problems we can solve them using parallel programming, but the problem is that when we have a problem with a sequential nature, I will give you some example. If let's say x, we say x equal to 2 minus, or for example 5 minus 2, then after that times 5 plus 1 like that. Okay, so here, can we divide this problem in multiple chunks?
Yes.
How?
5 minus 2.
This part can be taken in different taken as a sub problem, right? Then
Yes. Then after this it will be like the whole thing multiplied by 5.
so you mean this thing result
Yeah, multiplied.
multiplied by
multiply.
5. So this is another portion. Then
Yeah. Then plus 1.
okay, it can be, yeah, it can be, as you can say,
Okay.
as you can see here, it can be easily, right? But okay, let us think about it. If we divide the main problem into multiple sub problems, that means we need to do some processing, right? Right or not? To divide one main problem into sub problems, we need to do some processing, right? Alhamdulillah. Sorry, guys. Are you with me?
Yes.
Yeah. May I know your name, please? Your name, the student who asked me to take 5 minus 2.
Oh,
Yeah.
it's me. Singing.
Zing.
Singing.
Sing. Okay, sing.
You come.
Yeah.
Okay.
Yeah. What name you prefer?
Oh, you just call me I guess.
Okay.
Yeah. All right.
Okay. It's very simple. Yeah, very simple. If you take this big problem, you make it, you divide it into small chunks of problems, right? For example, you have one piece of maybe carrot. You want to put it or divide it into 4 pieces. You have to take the knife and you have to cut the thing to 4 pieces, right? That will cost you time.
Yes.
Am I right? Yeah, that
Yes.
will cost you time. And also, if the time is more than the original time that you need to solve the sub-issue, then better don't divide it in sub-problems.
I see.
Yeah, you understand what I mean? So if in this case, if you want to break this in 3 sub-problems, so here you have to do at least 2 or 3 instructions. You have to go through 2 or 3 or even more sometimes instructions, or that will require you like 3 or 4 cycles of the processor. Then your sub-problems will be ready. Then after that you start solving the sub-problems that will require extra instructions, and also every instruction will require an extra cycle of the processor. Then the processing time for solving that problem actually is going to be the time you take here to divide the big problem into sub-problems, then the time you consume to solve the sub-problems, so that the total time will be more if the problem is very simple like that. And also, because this problem actually is what they call it sequential, with the nature is sequential, so it's better to keep it sequential than breaking it into small chunks, then solve it using parallel computing. Okay, so here as you can see, this one, if we need to break it into 3, we need 3 cycles or maybe 2 cycles. Then after that we need 1 cycle here to solve this. This is 3. Then after that 1 cycle to multiply by 5. This is 4. Then another cycle to plus 1, which is 5. So if we solve it immediately as it is, see how it is going to cost us how many cycles. The first cycle is 5 minus 2. The second cycle is multiplied by 5. The third cycle is 2 plus 1. So it will cost us 3, while it will cost us 5 if we want to break it into parallel, sub-problems. Okay, you understand that? You understand what I mean? Yeah. The scenario, the problem is very basic, very basic. That's why the difference is 5 and 2. Only 5 and 2. So when we make it parallel, it becomes 5 instructions. When we make it sequential, it's only 3, right? But if the problem is sequential, its nature is sequential, and that problem is very huge, then we try to make it parallel, then it will cost us more than we think. So maybe instead of solving that sequential problem in 1 hour, if we try to solve it on parallel, it may take like 5-6 hours, something like that, if the problem is really huge. Okay, so it's very dangerous if we try to solve problems with sequential nature using parallel computing, because that thing will cost us a lot of resources consumptions, and also will cost us also power consumption, and the cost will increase, the time will increase, and everything will increase. Okay, so that's why we have to think twice before we decide whether we solve our problems using parallel or sequential. Okay? Okay, guys, is that clear?
Yes.
Do you need me to make other example for you?
No, don't think so. Don't think so.
You feel like you understand?
Yeah.
I don't think. Okay,
okay.
Let us take another scenario. 1 plus 2 times 2 plus 3, then times, we put 3 dots here, times until, for example, 99 plus 100. Okay. You understand this problem. So it will be 1 plus 2 times 2 plus 3 times 3 plus 4 times 4 plus 5 until times 99 plus 100. Okay, guys, what do you think? What do you think about this problem? Is it sequential based? I mean, the nature is sequential or parallel?
I guess it's parallel.
Mm-hmm.
Yeah, parallel.
So how we can do?
For like we can like 1 plus 2 and 2 plus 3 until 99 plus 100. It will be like one sequence, and the other sequence it will be like the multiply.
What do you mean?
Like so at first, right? If imagine we got like two computers, right? So I would like do 1 plus 2 first, then the other computer will do 2 plus 3.
Mm-hmm.
Then after that only like 1 plus 2 times 2 plus 3 and so on.
Uh-huh.
Yeah,
it can be, but if you can see, this is somehow similar to the previous scenario, right? Because here inside this we have a very simple problem, right? So if we take this, if we break this into a sub problem, that will cost us a very huge amount of overhead, right? Because we need how many how many sub problem we need to break into? Is about 100, right? About 100 sub problems. So that will cost us about 100 cycles of the processor. Then for every sub processor we have only one instruction. So instead we run that instruction directly, better than to divide it. Because when we divide it, we already consume one cycle, right? So it's better if we solve it because it costs only one cycle, right? Right or not?
Yes.
Yeah, so that's why here, to break this into small sub-problems, we have to think about something called granularity. So we need to know the granularity of our problem, for how much we need or for how many sub-problems we need to break our main problem into. So if you ask me, for example, if let's say we have a machine of 4 CPUs here. Okay. Let us take it step by step to make it clear and easy for you. If let's say we make it like as Ong said, if we break the small sub-problems, if we break the entire big problem into sub-small problems like this, 1 plus 2 is one problem, and 2 plus 3 is one problem, and so on. So we will have about 100 sub-problems, right? And every sub-problem has only one instruction. So there is no point actually to break it into sub-problems like that, because the granularity here is very fine. The granularity is very fine. Every portion of the problem has only one instruction. That means it's very fine, right? So what if we try to take this 100, we divide it by 4, because we have here 4 processors, 4 CPUs, so maybe we divide it by 4. So we can say like that, the first one is from 1 to 25. then 26 to 50, then 51 to 71, then 76 to 100. Okay, so in this case we increase the granularity. We increase the granularity of our subproblems. So every subproblem has minimum about 50 instructions, right? Because here we have about 25 plus operations and about 24 multiplications, right? So it's about 50. Okay, about 50 instructions per subproblem, right? So here, if we give every chunk of the problems here to a single CPU, so that CPU actually will spend about 50 cycles to solve this issue, right? This sub-issue. Then after that, it will cost us only one instruction here and one instruction here, then one instruction here. So the overhead is 3 operations after we finish, and also we have 3 instructions to divide or to break the main problem into subproblems. So in the parallelism overhead here is very little. Okay, it's only about 6 cycles. Okay, so here if we can see here in total how many cycles we need if we solve this issue as a sequential. So for every small sub problem here, we have one operation here inside the braces, and after that we have the multiplications. So for every sub problem we have 2 instructions. So 2 times 100 is about 200 instructions. About 200 instructions. Okay, 200i. I will say 200i. I try to make the font smaller. Maybe it can be easier to explain. Okay, so this thing, if we solve it sequentially, it will cost us about 200 cycles. And that 200 cycles, if every cycle is going to cost us about 2 seconds. So in total, how much it will cost us? It will cost us about 400, right? Is about 400 seconds. Okay, equal 400 seconds. Okay. What if we break it here into 4 chunks, and every chunk is given to a certain CPU? So in this case, if let's say the breakdown of the main problem will cost us 1, 2, 3, 4, 3 instructions, or maybe 3 cycles, then here what we have to put is 3. This is actually a roughly estimation of the operation cost. Okay, it's not exactly, but normally it's something like that. What I need now from you is to understand the main concept. Then after that, day by day, you will understand how it works. Okay, so to break down the main problem into 4 problems, we have to spend about 3 instructions. Then after that, we have inside every subproblem we have 25 sub operations. So in every sub operation will cost us 1 plus and 1 multiplication. So that will be about 50 instructions. About 50 instructions. Then after that, we have to multiply the result of every subproblem to the other, which will cost us about 1, 2, 3 circles or instructions. So also we need to spend 3 instructions here. So in total it will be about 56. So this 56 instructions times 2 seconds, it will cost about 112 seconds. Okay, you see how much we save out of our time. So here, if we run the entire problem over a single processor as a sequential problem, then it will cost us about 400 seconds. And here, if we break it into 4 subproblems and we give it to the CPU, then it will cost us about 100, which is the quarter of the total time we need to spend for sequential computing. Is that clear, guys?
Yes.
Yes.
So when I still didn't catch when we need to use sequential and when we need to use parallel.
Depends on the nature of the problem. Depends on the nature of the problem. I will give you one more example to understand. Okay, let me expand this and let us go here. Let's say we have this scenario. So A is equal to B plus C. Then D is equal to A plus E. Then F is equal to A times D plus G, for example. Then after that, H is equal to, for example, A times F divided by D. Okay, that's enough. What do you think here? Just answer me about the nature. Nature of the problem. Nature. First, nature is what?
Concurrent.
This one. Yeah. Do you know the meaning of concurrent? Concurrent means can run at the same time, right? Right or no?
Yes.
Yeah.
Yes.
Okay, let us take it. Let us take the first one and the second one. The first equation and the second equation. A equal to B plus C and D equal to A plus E. If let's say we give the two problems to different CPUs at the same time, then the first CPU can run because B and C is already there. Okay, they already have values, right? But here for D, it has to wait until A finish to get the result of A. After that, it can use it in its equation, right? So if let's say if let's say the time is like this, and this one is x1, this one is x2, x3, and x4. Let's say we have 4 processors here in our machine. So if let's say we assign CPU number 1 here, CPU 1, we assign whom let us make it clear, CPU 1, CPU 2, CPU 3, and CPU 4. Okay. Let us assume that on time zero here, this is time 0, second, and here for example, is 10 seconds. Then after that here, assume that we have 20 seconds, 20 sec. Then after that, we have 30 seconds. Okay, assume that every operation here, every equation will need 10 seconds to finish. 10 seconds to finish, roughly like that. Okay, so the first one, A, will need 10 seconds. D also to be calculated need 10 seconds. F needs 10 seconds. H needs 10 seconds. Okay, suppose that on time 0, we assign all operations, all equations to separate equations. So here we assign x1 to CPU 1, then x2 to CPU 2, x3 to CPU 3, then after that x4 to CPU 4 on time 0. Okay, let us check here. Suppose also that B is equal to 2 and C is equal to 5, for example. Okay, so this is the initial values for B and C. So in this case, if A wants to solve its equation, then the values and resources here needed are already available, right? B is equal to 2, C is equal to 5. So definitely it will become 7. So after 10 seconds, we can get the result of 7, right? We can get the result of A. Right or not, guys?
Yes.
Yes. What's about D?
Yes.
What's about D at the time 0? At the time 0, D does not have, what we need to do is also, for example, E is equal to, for example, 4. Also, G is equal to, for example, 11. And what else? Okay, that's all. Okay, so in this case, for D, at the time 0, D has only the value of E, but no value for A yet. Right or not?
Yes.
Correct.
Yes. So here, D cannot be solved until A get ready, right? And A to get ready need about 10 seconds, right? So that's why here, this guy actually will continue calculating until here, right? So this is to calculate x1. Then this CPU2 is going to be waiting. It will hold the value of E and it will wait for the value of A until it get ready, right? So after A is ready, then D can be calculated, right? So here we can, at this moment of time, we can calculate D, right? Right or not, guys?
Right.
Yes.
Yes.
Okay, what's about if at the time 0? At the time 0, if cannot get the value of A yet, right? And also cannot get the value of D. And only can get the value of G, right? So can we calculate F at the time 0?
No.
Okay, what if we try to calculate it at the time 10? So at the time
No.
10, A is available, right? And G is available.
Yeah.
What's about D? D is not available. Why? Because D need about 20 seconds to be ready. So when we can calculate the F is after 20 seconds, right or not?
Right.
Correct.
Yeah, so here we need about 20 seconds to calculate the F, right? Okay, let us check H. Okay, H at the time 0, A is not available, F is not available, D is not available. So at time 0 cannot do anything, at time 5 cannot do anything, at time 7 cannot do anything, at time 10 A is available. But F and D are not available yet. So at 10, 12, 13, 15, 16 cannot. It's impossible to calculate the H, right? What's about time 20? At time 20, D and A are available, right? But F is not available yet. So F to be ready is after 30 seconds, right? So H can be start calculating after 30 seconds. So in this case, the thing will be like that. Okay. Do you agree with me?
Yes.
Yes.
Yes, okay.
Okay, now based on this diagram, based on the diagram that I draw just now with you, is the nature of this problem parallel or sequential?
Sequential.
Yeah, sequential. Event two, we separate it in multiple subproblems and we assign it to different CPUs. It cannot be solved as parallel issue because its nature is sequential. You understand?
Yes.
Yeah. Anyone has unclear things or maybe unclear thoughts or yeah. Anyone has a problem?
On total,
Yes.
at the 0 second, so the ADFH is 0, right?
What do you mean?
At the
At the 0 second,
0 second,
time 0. Yeah.
yes, time 0, the
Yeah.
ADFH is 0, right?
Yeah. Still has no value. Still has no value.
Okay.
Yeah.
Okay.
Yeah. They will keep their initial value until they could get the new value after they calculate. Okay. Depends on how you do the program, because in programming sometimes you make integer a, and sometimes so if you make it integer a because a is a value based, is not reference based, so it must have a value. So the default value for for value based integer is 0, even though if you don't initialize it. So in that case, a will be 0. But if let's say you make string a and you finish, you did not assign any value. So in that time, a, because a is a reference type, string is a reference type. So in this case, a will get the value of null, not 0, null. Okay, and null is not a value. So it depends on how you write your code. Okay. Actually, this thing is not in our scope now. Later, when we go to the programming, then we can explain and see how it can work. Okay. Anyone else have a question?
So far, no, Doctor.
Okay, that's good. So here the nature is what? Sequential, right? Sequential, not parallel.
Yes.
Okay. Okay, let me give you another example. Okay, what's about I think all of you knows the arrays, right? You all know the arrays, right?
Yeah.
Yes.
What if we have array like this? Sorry for my board drawings because I'm using the paint here. So if let's say we have an array which is like that, okay? Then what we want to do is like that, or CV, Then we need another array here, and we want to put like this, multiply the arrays. Okay, can you tell me what is the nature of this problem? Anyone can tell me?
I think parallel,
Why you think it's parallel?
because one CPU can solve one array, and another CPU can solve another array, and then it can just times together.
No, it's not like that. So if we have three arrays, multiplication of three arrays, what we can do? We need three CPUs in that case, right? Yeah, this is not the case. The case, actually, anyone else have a question? Has an answer? Just try. Don't be shy. Just try to answer. Anyone has an answer? No. Okay, how we can multiply arrays? Oh, sorry, not arrays. Matrices. How we can multiply matrices? So what we need to do is to take the first row, multiply by what?
First column.
First column, right? So this is a subproblem here. So the first row with the first column is the first subproblem. Then the second row, I will use different colors to differentiate between them. Oh, that one is already changed. Okay. Oh. Okay, the first column, first row with the first column from the second matrix is going to be given or going to be treated as the first subproblem. Then the second row here with the second column actually is going to be treated as the second subproblem. Okay, the question here, is there any relation between the first subproblem and the second subproblem here? Is there any relation?
Yes.
What is the relation? Referring to this scenario, is it like the second row will wait until the first row finish or not?
Oh no.
No, right? Yeah,
No,
because
no.
to calculate the second row with the second column, we shouldn't wait for the first row and the first column, right? So we can,
Yes.
at the time 0, we can start calculating each row with each column, right? So that's why the subproblems here are independent. Each subproblem is independent. We don't have dependent problems like this because this scenario is fully dependent on each other. Okay, so that's why we cannot solve the second one until the first one got solved, right? This is what they call it, dependent. Okay, this one dependent scenarios are sequential. For sure, 100%, 1000% is sequential. Even to no matter how big they are or how small they are, their nature is sequential because they are dependent. As easy as that, okay? But for this, because the subproblems here are independent, so the nature can be solved in both cases using sequential and using parallel. Okay, we can solve it using the two cases, sequential or parallel, but sequential will get more time, will need more times to solve, because at every time, at every single point of time, we will solve only one instruction. But if we break it into multiple sub-problems, then each sub-problem can start at the same time, and it can do its own processing, and it can be solved independently. So at the end, after we finish the calculation of every row, then finally we can combine the result together, right? To solve the entire operation. Okay, so this is totally 100% is parallel. Okay, why parallel? Because it's independent. Its nature is independent subproblems. Here, I mentioned something called granularity, right? Right or not? Yeah. If we make it very coarse, because granularity is it has two things: very fine and what they call it. I want to write it: fine and coarse. Okay. Oh, sorry, I'm writing in other place. Okay. Okay. Fine and coarse. Okay. So when it's fine and when it's coarse, like that, fine and coarse. So we can say the granularity of the system is fine if we break the small subproblems into a very small number or a group of instructions. So for example, if we break this matrices multiplication into very fine granularity, so in this case we have to take one item at a time. So let me take get a circle here. So we take this multiplied by this. So this is called the first subproblem. And then the second subproblem is going to be the second item multiplied by the second item from here. Okay, so in this case, this is the finest granularity that we can have in our system. The finest granularity that we can have in our system. Is that clear, guys? So we cannot break the problem in smaller operations than this. So the smallest thing is to take item by item, cell by cell, right? But if we want to make it very coarse, so in this case, we solve the entire problem at once. So we consider it as only one problem. So in this case, it will be solved as sequential, and also it will be solved as one chunk. Okay, as one chunk, one problem. Okay, we have some things for sure. We have some things here at the middle between the fine and coarse. So it can be semi-fine, semi-coarse. It can be middle between fine and coarse. It can be or somehow or somewhere between fine and coarse. So how we can decide this? Actually, it depends on the nature of the problem. Depends on the nature of the problem. So for the scenario of matrices like this, it's better to take it as one row by column for each subproblem. One row by column for each subproblem. Okay? So in this case, it's not fine granular, and also it's not coarse granular. Okay? So it's something at the middle. So the point of granularity actually is very important to find the optimal time that can be consumed to solve the main issue. Can be consumed to solve the main issue. So for example, if we go to this problem, last time one of you said we can take summation as a sub-problem. This is very, very fine. So in this case, actually, it's going to cost us more than 400, right? More than 400 seconds, because it will cost us 400 seconds if we solve it sequential like that, as once. So if we solve it as a one problem sequentially, it will cost about 400 seconds. But what if we break it into very fine sub-problems? Okay, are you with me, guys? What if we break it in very small, very fine granularity manner? So in that case, we need to break this into small problems, right? So this is one problem, second problem, third, fourth, then until 100 problems. So to partition or to break down this main issue into sub-problems, it will cost us about 100 cycles. 100 cycles. Okay, let us calculate it. So it will cost us about 100 cycles. This is only to break it down into sub-problems. Then after that, every sub-problem will cost us 2, right? Will cost us 2, because this one is, will cost us only 1, right? So this will be plus 1. Then after that, what we need to do is to have about, this one is one instruction. One instruction to solve one sub-issue, right? Then after that, we need to do how many multiplication? About 100, right?
99.
After we finish.
99.
Let's say 100 to make it easy. Okay, so yeah, because as I said, it's roughly estimation. It's not that serious. So it's about 100 multiplications, which will cost us about 100 instruction, right? So this will be equal to how many instructions? It will be 201, right? 201 instructions times 2 seconds for each. It will be how many? It will be about 404, right? 404. So what we achieved here, even if it's still 400, it's still similar to the sequential, right? We cannot reduce the time here, right or not?
Yes.
Yes. So what's the point to have all of that headache writing that parallel program? Because writing parallel program is a very big hassle, you know, it's very big problem to handle, very big problem to design, and you need to do a lot of optimization, you need to do a lot of memory optimization also, and you have to consider a lot of scenarios, a lot of issues. It's not an easy task, okay? So what we got here is wasting our time writing parallel program that can give us 0 time saving, right? 0 time saving. So it's time wastage, right? We better don't do that. So how we can solve it? Because now this problem can be solved in parallel, as I said here. In this scenario, right? As I said, it can be solved as a parallel, right?
Yes.
But at a certain level of granularity. At a certain level of granularity. So if we make the granularity very fine, so that one main issue will be divided into 100 sub-issues, which is very fine. In this case, we cannot save anything. But if we increase the granularity to make it maybe 20 or 10 sub-problems, or even 4, as you can see here, 4, because we have 4 processors here. We break it into 4 sub-problems. We can see here the benefit of time saving, right? the benefit of using parallel program to solve that issue. Okay, so the granularity actually is a key to help the system designer or the system programmer to to optimize or to shorten the time of computing or to shorten the time of processing. So it's very important aspect. Okay, granularity is very important thing to consider. You have to understand it. You have to try many scenarios. After we finish this class, please try to sit with yourself when you have time and try to think about some simple cases or some simple problems that you have in your daily life. Okay, and try to solve it. Try to break it into a small number of sub-problems or even a very big number of sub-problems, and see how you are going to save the time. See how you are going to save the time. Okay, one more thing here, because when I do the estimation here, I'm not sure whether you understand what I'm doing here or not, because in here we wrote 100i, right? 100 instructions, and then we have one instruction, then after that 100. So this one actually is the pre-processing that we need to do, actually. Pre-processing to prepare our main problem to become broken down into sub-problems to fit parallel processing. Okay, so this is what they call it, pre-processing. Okay, then after that we have the processing required to solve every sub-problem. Then after that, what we need to do is to combine the entire system or the entire number of results that comes from the sub-problems together to get the final result. Okay, is that clear, guys? So when you calculate or you do estimation, you have to think clearly. You have to think in a correct manner. Otherwise, your estimation will become wrong. Okay, any question, guys, before I move?
No question.
Okay, hopefully you understand. So I only take one slide. Don't worry, yeah, because I already explained more than the slides we need in this class. So what we need to do now is to go through the slides quickly to recap with what I have explained. Okay, so here in this slide, what is parallel computing? So here we have traditionally software have been written for serial computation. So to be run on a single computer that has only one CPU. A problem is broken into a discrete series of instructions. So instructions will be given to the CPU one by one. So that will be every instruction will be executed one after another. Then only one instruction may execute at any moment of time. Okay, in the simplest sense of parallel computing is the simultaneous use of multiple compute resources to solve a computational problem. So for example, if let's say we have multiple CPUs, then we can have independent problems. So every problem can be sent to the CPU. That problem will be broken down into instructions. Then for this level of the problem itself with a certain CPU, for this CPU, it can handle only one instruction at a time. And that CPU can handle only one instruction at a time, and this one can handle one at a time, this can handle one at a time. So at one time, all processors can handle four instructions at a time. So the rate of processing here will become 4 per cycle, right? 4 instructions per cycles here. While here, only one instruction per cycle, because we have only one CPU here. So the rate is very important to reflect the speed of the processing or the computer. Okay, so in this case, in the parallel, we have one instruction per cycle. One instruction per cycle. Here, we have n instructions per cycle. And in here could be the number of cores, could be the number of CPUs, and whatever. Okay, depends on what resources you need to have to solve your problem. Okay, is this point clear?
Yes.
Okay. Very simple, right? Very simple idea. Then how to implement it, that's another thing. Later we can discuss about it. I can explain to you, and you can learn step by step how to make parallel program. Okay? But for now, what we need to understand is only the abstract idea of how parallel could work. And what is the difference between parallel and sequential. Okay? So here, parallel computing is the simultaneous use of multiple compute resources to solve a computational problem to be run using multiple CPUs. Okay? A problem is broken into discrete parts that can be solved concurrently. So as you can see here, a problem is broken into discrete series of instructions. So here, the thing is very fine, right? The granularity is very fine in terms of the same problem, but in terms of the main problem, actually the problem is solved as one problem, so it's already coarse, very highly coarse. Okay. Okay. Each part is further broken down to a series of instructions. So as you can see, the main problem is broken into 4 parts here. 1, 2, 3, 4. Then each part will be broken into sequential or a series of instructions that will be solved as sequential. Okay, so even though here we are talking about parallel computing, we still have to do kind of sequential work here. Okay, inside each problem, inside each subproblem, we may see solving instructions sequentially. Okay, so the thing is actually a hyper solution or a hyper technique because we cannot have 100% parallel that does not have any sequential operations. It's impossible to happen. Okay, because that will create more overhead than the overhead needed to solve that issue. Okay, so in most cases, or in all cases, it will be like a mix between parallel and sequential. But the level between sequential and parallel has to be decided based on the granularity of the program. Okay, so the granularity will decide whether we rely more on parallel or more on sequential, because the granularity is going to play the role of balancing. Okay, so it will play the role of balancing between the parallelism and sequential. Okay. Instructions from each part execute simultaneously on different CPUs. So here, every problem will be broken into sequential instructions, and that sequential instructions will be run over a certain CPU and will not be related to the other instructions belongs to the other CPU or assigned to the other CPU. So here, parallel computing resources, the compute resources can include a single computer with multiple processors. So we can have like one PC or one laptop with the i7 that has 4 cores maybe, and each core is working as an independent processor. So in this case, we could have 4 instructions per time per cycle, or maybe 8 instructions per cycle, and so on. Depends on the architecture we use for our processor. And also it can be a single computer with multiple processors. and some specialized computer resources like GPU, FPGA, and so on. Also, nowadays we have something called GPU, and GPU can do processing also, similar to the processor. So in this case, like my own laptop has 4 cores in the processor and 2 cores in the GPU. So in total, I can run 6 instructions per cycle. Okay, so that could be very fast, and it could help you run your applications and run your programs very quickly or very fast. Okay. The third point, an arbitrary number of computers connected by a network. So this one actually, when we have multiple computers connected by a network, and that computers are controlled by one managing software to solve some issues together, this is what they call it clusters. Computer clusters. So many computers connected by a fast network to handle certain problems, to work as an entire or as a big computer controlled by only one software. So this is what they call it, clusters. Okay. Also, it can be a combination of all above mentioned scenarios. So it can be a cluster that have multiple computers, and every computer can have multiple processors and multiple GPUs inside it. So it will be a combination of all of the things together. Okay, is that clear, guys?
Yes. Clear.
Okay. The computational problem. Here, the computational problem usually demonstrates characteristics such as the ability to be broken apart into discrete pieces of work that can be solved simultaneously. This is what I have explained here, so I shouldn't explain again, okay? So you already understand what does it mean. So if the problem is like this, so there is no point actually to break it down into sub-problems, because the nature of it is already sequential. But if the problem is like this, like multiplying arrays, then it's worth actually to break it down into sub-problems and handle it as a parallel or as concurrent problems. Okay? So this will save the time, will increase the speed of the processing. Okay? Here, execute multiple program instructions at any moment of time. Execute multiple program instructions at any moment of time. So when we have a problem that its nature is concurrent, so it can be broken into pieces, and that pieces could be run separately on different CPUs, right? So in this case, the number of instructions will increase, right? The number of instructions executed per cycle will increase, as I said here. So if we make the problem as one problem, it will be one instruction per cycle. And here, if we broke it into multiple parts, it will be about 4 instructions per cycle for this scenario. If let's say we have 8 CPUs, then it will be 8 instructions per cycle. If we have 16 CPUs, it will be 16 instructions per cycle. So the rate will increase, and if the rate increases, the speed will become faster, okay, and the time will become lesser and lesser. Okay, so this is how the parallel things work. Also to be solved in less time with multiple compute resources than with a single compute resources. So whenever we increase the number of resources like processors, so if we make it one single processor, it will be one instruction per cycle. If we make it 16, it will become 16 instructions per cycle. So the relation between the number of resources actually is a direct relation to the speed. So whenever we increase the resources, the speed will increase. Okay? And the time is the opposite. The time will reduce. Okay, so this is how it works, and this is the relations between the metrics. Okay. What we have here, parallel computing is an evolution. So what for? Parallel computing, what for? Why we need to use parallel computing? I already explained actually to you, but let us go through the slide. We see if there is any point that we does not cover. So parallel computing is an evaluation, is an evolution of serial computing that attempts to emulate what has always been the state of affairs in the natural world. So many complex interrelated events happening at the same time, yet within a sequence. Some examples here. So in the real life, we have many scenarios in our daily activities are actually based on parallel or works concurrently at the same time. So, for example, the weather and ocean patterns, also rush hour traffic. So in the rush hour traffic, many people are driving their own cars independently, right? And also during that time, while X and Y driving their cars safely, maybe Z is parking at the roadside, maybe W has an accident. So all of that events are running at the same time concurrently, simultaneously. Okay, so this is based on our daily life. Also daily operation within a business. So maybe if you are in an office with five people inside the office and everyone is doing his own task, that means multiple tasks at a time, right? So that's also another scenario of concurrent system. Okay, building a shopping mall. So if let's say we are building a shopping mall, so maybe we have tractor doing something. We have some person is welding, another person is building, another person is doing whatever, maybe using drill, maybe whatever else. So many tasks at a time, right? Also ordering a burger at the drive-through. So while you are driving, you can make an order, and also the staff of the restaurant, they can make the burger. So how many tasks at the same time? Many tasks at the same time. Okay? Traditionally, parallel computing has been considered to be the high end of computing and has been motivated by numerical simulations of complex systems and grand challenge problems such as weather and climate, chemical, blah, 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 is something similar to the last slide. So I'm not going to repeat the same thing. Okay, we still on what for? Today, commercial applications are providing an equal or greater driving force in the development of faster computers. These applications require the processing of large amounts of data in sophisticated ways. So example applications include parallel database, data mining, oil exploration, web search engines, web-based business services, computer-aided diagnosis in medicine, many other applications, okay? Ultimately, parallel computing is an attempt and effort to minimize the processing time. It's to minimize the processing time. So we'll get things solved faster and improve the quality of our systems, because the response time of the system is required to be very short. So we need to shorten it as much as we can, okay, to serve us quickly and to make our life easier, okay? Why parallel computing? Why parallel computing is a great question. So this is a legitimate question because parallel computing is complex on any aspect. Okay, so if the parallel computing is complex, why we still need parallel computing? Because we still need to save time, right? As I explained, we still need to save time. we have to pay that cost, actually, of complexity. We have to spend time to build very complex systems that can handle parallel problems, okay? To save the time, to solve larger problems maybe, or to provide concurrency, so to allow multiple users maybe to do their tasks at the same time or whatever, okay? So there are many targets or many reasons why we still need to use parallel computing. Okay. Other reasons might include taking advantage of non-local resources, using available compute resources on a wide area network, or even the internet when local compute resources are scarce. Okay. So here also, based on parallel computing, we can utilize other resources which can be remotely located in other places, or maybe located on the cloud or whatever. Okay, so that can help us achieve our tasks faster and faster. So the cost saving also can be, the cost can be reduced. So using multiple cheap computing resources instead of paying for time on a supercomputer. Actually, supercomputer is the computer that has very huge number of resources, processing resources like CPUs, GPUs, and so on. So that is going to be very high, very highly costing. Okay, so instead we can use normal computers, normal personal computers, and connect them together using a fast network, and manage them using a single software to run them as a cluster to handle big problems. Okay, so this is another solution for parallel computing. Also, this point actually allows us to utilize the what they call it, the outdated computers. So if, let's say, we have a lot of second-hand computers that's already outdated, so we can get benefit out of them. So we can cluster them, we can still use them to handle big problems, okay, using clustering softwares. Overcoming memory constraints. So single computers have very finite memory resources, so using the memories of multiple computers may overcome this obstacle for large problem. They're still talking about the cluster in the previous point. Limitations of serial computing. So this thing actually limits the serial computing, limits to serial computing both physical and practical reasons, pose significant constraints to simply building ever faster serial computers. So here, if we want to use serial programmings always to solve all problems, even if we have very fast computers, then the result of our application will be very slow. Why? Because the physical resources that we have still cannot handle our issues in parallel way. Why? Because we still use serial computing, right? So in this case, the software will limit the capability of the physical resources. Okay. Also, we have the transmission speed. Actually, the transmission speed is the speed of data to be transferred among the processing resources. So if, let's say, we have four CPUs in our computer, then if CPU 1 wants to pass data to CPU 2, if the connection is very slow, then the entire system will become slow. Okay? So that's why the network is very essential. The network is very important to be fast. It's very important to be fast to improve the result of our applications, because all applications available nowadays are a mix between software and hardware, and also a mix between computers and networks. So for example, YouTube, or maybe Google Drive, or whatever, it's a mix between processing units and networks, right? So if the processing units are very fast and the network is very slow, then the result of YouTube will become very slow to the end user, right? So that's why we need to take care about the processing units and at the same time the connectivity between them. Okay? Limits to many miniaturization. This one is to what they call it, to make things small. The meaning of this word is to make things small, like minimizing the size of chip. Okay, so processor technology is allowing an increasing number of transistors to be placed on a chip. However, even with molecular or atomic level components, a limit will be reached on how small components can be. So that's why if we want to handle the things as serial, then we will have a limit, physical limit on the chip itself, because the chip cannot handle a very huge number of components. That's why they try now to make multiple chips, like multi-cores and so ever, whatever, to run at the same time concurrently to handle parallel problems. Then economic limits. So it's increasingly expensive to make a single processor faster. So if, let's say, we want to make a single processor faster than a multi-processor machine that has, for example, 4 processors or 80 processors, we want to mimic that performance using only one CPU. That CPU will become very expensive. Because it will need to use a large number of components. So using a large number of moderately fast commodity processors to achieve the same or better performance is less expensive. So that's why we can use large number of processors, for example, 8 CPUs or 16 CPUs on the same machine, better than to put 16 CPUs or the capability of 16 CPUs together in one processor. That will cost us more. Okay? The future during the past 10 years, the trend indicated by ever faster networks, distributed systems, and multi-processor computer architectures, even at the desktop level, clearly show that parallelism is the future of computing. So parallelism is very important. It will be multi-forms, mixing general purpose solutions, your PC, and very specialized solutions as IBM cells, clear speed, GPU from NVIDIA or from whatever vendor. Okay, so here this is the last slide for today. So who and what? Here you can see the top500.org actually provides statistics on parallel computing users. So as you can see here, the sectors that uses high performance computing, which is based on parallel computing and distributed computing. So as you can see here, there are a lot of sectors like energy, education, research, for example, software, telecommunication, retail, whatever in our life is here. So all the sectors in our life are based on the HPC, and you can see here the variation between sector to another. So some sectors rely more on parallel computing, while others are not relying too much because of the nature of their problems. So if their nature of the problems are sequential, they cannot rely on parallel computing. Okay? So here you can see the academic is this portion, and also the industry is that portion, is about 50%, is 50% actually. And also here, what they call it, research actually is 24, Okay, so from here you can see the significance of using parallel and distributed computing, because parallel and distributed computing is very necessary and can save our time, can serve us quickly, and can improve the quality of our life. Okay, that's all, guys. And Alhamdulillah, we finished on time. If you have any question, please let me know before we close this class. Okay, any question?
No.